Welcome to Lab 2. Let's get this thing going. So I've opened up the lab, and remember the first thing that I'm going to do is I'm going to save a copy to Drive. So this is going to open up another tab with the copy of this thing. Now when I edit this, things will work out nicely. I can save it to my drive. Everything will be working out great. I'm going to close this little banner. And let's get this thing started. I can add my name and the due date here, but I'm just going to jump right into what we've got going on. So in this lab, we're going to be taking a look at three different things. We're going to be looking at improper integrals, we're going to be looking at sequences, and we're going to be looking at series. So for the improper integrals, we're going to go back to working with Riemann sums, but now we're going to have a little bit of an issue in that our limits of integration are going to have some problems. So we're either going to be looking at getting really close to a vertical asymptote, so I have to be careful with how we set up our rectangles, or we'll be looking at having infinity in our limits of integration, meaning we're going to have to look at limits as we approach these limits of integration, and we're also going to have to look at a limit as the number of rectangles goes off to infinity. So we're going to have two large values to help approximate both of these limits. One to approximate infinity in the limits of integration, another one to approximate the infinite number of rectangles that we're going to be using in our Riemann sums. Let's get this thing running. So I'm going to import NumPy and Matplotlib. That should work out great. And now we're going to jump into this infinite width integral that we have. So notice we're going to have this function. We're going to go ahead and integrate from 0 up to infinity. We should be able to just do this by hand maybe. This one's a little bit tricky to do. So this is a good one to do in Python here. So I've got my function. F of x is x cubed times e raised to the negative x squared, and you'll notice I'm setting up my limits of integration here. I'm going to go from 0 up to 10,000. Now again, I'm supposed to be going up to infinity. I'm going to use 10,000 as a representative for that. And now I'm also going to use n to be, what's this, a million? The reason I want to make so many rectangles is because I want a lot of rectangles in between each integer value. So the larger I make this value of b, the larger I should make this value of n, so that I get a nice fine partition that I'm using. From there, things go pretty nicely. I'm going to go ahead and set up my delta x. I'm going to set up a bunch of x values and just plot this thing just to see what we have. Okay, so that graph is not that useful to look at. Remember, we're plotting this thing out to an x value of 10,000. You can see our function starts up pretty high, but very quickly we approach that horizontal asymptote. This almost just looks like a corner. So let's maybe just take a look at the graph between 0 and 20. Let's see what's going on there. Okay, we can see why that earlier graph was so weird. By the time we hit an x value of like 3, we have essentially hit our horizontal asymptote. Y is very close to 0. And so if we went all the way up to 10,000, most of our function is just really close to 0. So it looks like this horizontal line. So if we just sneak a little bit closer to that early part of our function, we can actually see the graph. This is where most of the area under our curve is going to be. The rest of this underneath the tail is hopefully going to be very tiny and won't actually impact the total area that much. All right, now be careful though, because when we actually calculate the area, I do want to go out all the way as far as I can into that tail. So I'm going to go back to this limit of integration going out to 100,000. Just because the graph isn't that helpful, it doesn't mean I don't want to account for this area in my approximation. I'd like to go out as far as that's as reasonable. I'm going to just set delta x to be 0.01. This is the same as if I set n to be really big and then define delta x later from there. It's all the same thing. I'm going to set up my partition now from A up to B, counting by 0.01s, and then this is just a basic area under a curve, so my sum formula is very easy. I'm just looking at the function values at these partitions, and I'm going to multiply that sum by delta x. It's going to take a little bit to run, because as you noticed earlier, when we have to do so many rectangles here, it can kind of take a little bit of computational power. Now this is an approximation of our area, and hopefully we can use this to get a general idea of what we've got going on. Now we can use our integration techniques here and do this. It's difficult to do. We might have to do some U substitution and then some integration by parts, but it's not impossible for us to do it. So what I would do is recommend that you just give this a shot. See if you can do a U substitution. Maybe we pick like x squared or negative x squared as u, set up a u and a du, go from there, and then you'll have some integration by parts left over after that. Hopefully, when you do that, and then you actually apply the limit for the improper integral, you're going to get something very close to this approximation. Let's do a similar one with an infinite height now. You'll notice this function has a vertical asymptote at x equals 1, which is our limit of integration. Oh no, we have this infinite height in our interval that we're looking at, so we're going to have to go ahead from here and set things up. We aren't going to be able to do a left partition here, because if we do a left partition, our first point in the partition is 1, and our function value there is not defined. So what we're going to do is set up a midpoint partition. I'm going to go, or actually no, this is a right partition, sorry. I'm going to start at a plus delta x, just so the right end of that first rectangle. And now I'm going to count out to b plus delta x by delta x's. So if we set that partition up, it's going to start with 1 plus this tiny delta x. It's going to count up to and including 3 now, because we've told it to count a tiny bit past, but not including that. So 3 will be the last value in here, and then we can go ahead and plot this thing. You'll notice that the plot of it looks, again, not super helpful, because our function just shoots down really, really quickly. All right, we're plotting this function value really high up, because this is essentially our vertical asymptote. It might be a little bit easier to start with something a little bit over here in our graph, but oh well. Let's go ahead and approximate the area. We've got the partition already set up nicely to do this, so we can go ahead and just do the same area formula. And that's an approximation of the area under that curve. There's going to be some more interesting things that you're going to look at here. You're going to look at another infinite width one where you may not actually be able to double check this by hand. In this one we can. And maybe later we'll do one that you can't. I kind of forget. I'll look later. And then we're going to do another one with an infinite height. That's also a little bit tricky, I think. You'll have to split things up at the asymptote. It should go pretty well. Let's pivot a little bit and talk about sequences. This is a sequence that we have. -1 raised to the n plus 1 over n. This is a nice little alternating sequence. We call this like an alternating harmonic sequence where the denominator just marches up 1, 2, 3, 4, 5, but our numerator flips back and forth between positive and -1. So you can notice that our first value, when you put n equals 1 in there, we get -1 squared, which is +1 over 1. So we have 1. And then when n equals 2, we have -1/2. And then when n equals 3, we have +1/3, and then we'll have -1/4, +1/5, etc., etc., etc. All of the even denominators are negative. All of the odd denominators have positive terms on those. So that works out pretty well. Since we talked about these things kind of being functions, where our inputs are just restricted to integers, we'll define it as a function. So this is sequence A, and you'll notice I'm just defining it as -1 raised to the n plus 1 over n. We can go ahead and plot this thing. Now the nice thing is that matplotlib can plot with little points. So I'm going to go ahead and plot the first 100 terms here. So again, I'm using NPA range from 1 up to 101. I'm not defining a step size because the default step size is 1. So you don't have to define that if you're just going to be counting by ones. Now remember, this is actually going to count from 1 to 100 because we're not going to include 101. And then we'll plot this thing. This little tidbit here, you can go up and see what this means. The R stands for red, and the O stands for a circle. And we'll go ahead and, oops, I forgot to run this chunk of code. There we go. Now we've got our sequence defined. You can see it says, hey, sequence A is not defined. Go run that. Now we'll run it. And hey, look at, here's our sequence. If you change this little code here, you can change the R to a G, and suddenly you'll have green things. You can change the O to a period or a dot, and you'll have smaller dots. And if you use commas, you'll have even smaller points. You might not even be able to see that on our video. I'll go ahead and go back to red circles, nice big points, so we can see what's going on. That's our sequence for the first 100 terms. Okay, so you can notice, like, it might be a little hard to see some detail, so maybe in some plots we'll want to change the point size here. We're maybe, with sequences, more interested in what the tail of the sequence is doing, because we care about the limit as our terms go off to infinity, or the index, I should say, goes off to infinity. We care about this limit right here. So maybe what we'll do is plot the tail. When I say the tail, I just mean, like, I don't know, somewhere really far down the sequence. So I arbitrarily chose to start at 500, and I'm going to go up to 10,000. So I've got 10,001 here that I should be plotting this up to, right? Because then it's not going to include the last point. And then we'll go ahead and run this thing, and I'm going to put a dot here first. So you can see these actually look like lines. These aren't actually lines. These are dots that are so close together that they look like it. I'll go ahead and put it back to commas here so they're even smaller, and it still looks like that. We can change the starting point if you'd like to, I don't know, maybe 5,000. I'll change my plot thing here to go from 0 up to 5,000 as well. Or sorry, it's at 0. I'm going to go from 5,000 to 10,000 here on my horizontal line. And it still looks like these are lines because these points are so packed close to each other. But we can at least see that the difference in the outputs, the actual sequence terms, are very, very small, right? And again, visually we could see that this thing is approaching this horizontal line at 0. We have really good evidence here that the limit of this sequence is 0. Now we could go ahead and just do that by hand. Maybe we'll have to use a little squeeze theorem to account for the alternating sign. No big deal. We'll look at the top line, we'll look at the bottom line, or I guess sequence, and we'll notice that both of those sequences go to 0, and so the alternating version is going to as well. Really good evidence that this sequence converges to 0. Then we could take a look at the series that we get. Same formula, right? So now instead of looking at the sequence of terms, we're adding all those terms together. And now we'll remember that, hey, what we care about is the sequence of partial sums. So what we're going to have to do is not plot the sequence of terms, but see if we can construct some partial sums. There's some built-in functions that will do this for us, which is great. So here I've got a sum function. I'm going to add up the sequence terms from 1 up to 11, not including 11. So this is the first 10 terms. And probably I should put a little print statement here, but if it's only one thing, it prints the last thing in there anyway. So here is the sum of the first 10 terms. Now, that's probably not an interesting partial sum for us, right? We care about the sequence of partial sums. And so what we can do is use this cumulative sum function. That's what cum sum stands for. Let me show you how this works. The cumulative sum function takes in a list. Now, in this one, I've just picked a random list that's short so we can see what's going on. But eventually, we'll do it with sequence terms. And what it's going to do is it's going to output a sequence where we're looking at the partial sums of the list. So it's going to do 1 plus 1. That'll be 2. And then it's going to do 1 plus 1 plus 0.5. That'll be 2.5. And then it's going to do 1 plus 1 plus 0.5 plus 0.25. So we can see our first partial sum is just the first term. And then it's the first 2 terms. And then it's the first 3 terms, and then it's all 4 terms added up. So this is a sequence of partial sums of this list. We're going to do that with the partial sums that we built from this sequence here. So instead of plotting a sequence itself, we're going to plot the sequence of partial sums. This says let's graph the first 30, but then I'm doing 50. Let me go ahead and just change this to 50. All right, so now I'm going to set up a list of indices. This is just a list of numbers 1 through 50. Remember, it doesn't include the last value, so we go up to 51. Then I'm going to build the partial sums. That's going to be the cumulative sum of the sequence terms for those indices, right? So instead of looking at just the sequence terms, I'm going to be looking at the partial sums of these things. You can think cumulative sum is really partial sum. I'm going to save those, and then I'm just going to plot. Let's plot the indices by the partials. And we're going to do blue with a little dot here, so kind of small points. And this is what the partial sums look like. Notice it looks like they're approaching something, but not 0, which should make sense because we started with 1 minus half plus a third minus a fourth. So it's not like we're going to be adding up to 0. When we combine all these things, 1 minus a half is half. And then when we plus a third, we're going to go up a little bit and then down a little bit and up a little bit. And so we're trying to figure out where do we actually end off. It looks like we're somewhere around 0.7, right? Although this isn't right. Looks like here there's supposed to be a horizontal asymptote between 0.55 and 0.6. That's wrong. We'll have to figure out what's going on with that. And here it is, 0.68. I probably changed the function here. So maybe I'll just say 0.65 and 0.7. I probably changed what sequence I was looking at when I did this and just forgot to update. So here we can add up the first 50 terms. Notice now I'm just using a sum because I don't need the whole sequence. I just need the last term of the sequence, all of those terms added up. I only need the sequence when I'm plotting them. But what might be more helpful is to look at more than 50 terms. Let's look at like the first 10,000 terms added up. And then we'll look at the first 50,000 terms, and then 100,000 terms, and then, oh my God, what is this? 5 million terms? Jeez. Let's go ahead and run this thing. It did not take that long to add up all of those terms. Now, notice this. These are all pretty similar to each other, and especially these last two. These don't change until what, the 1, 2, 3, 4, 5th, 6th decimal point. So these are only off by a tiny bit. That means the sum of the first 100,000 terms versus the sum of the first 5 million terms. It's a lot of difference in the number of terms we're doing. That total sum doesn't actually change that much. It barely changes at all. If we're thinking about limits here, we're approximating the limit as this value goes off to infinity, right? The term index. And so this is a really good approximation. And also, the fact that these don't change is really good evidence that this series converges, because those partial sums aren't changing that much when we get really, really far. What it does is it converges actually to natural log 2, and here we can see how close it is. Because we know that this converges to natural log 2, whether you've seen that in the text or I've got proofs that maybe we'll post on Discord or something like that, we'll take our approximation, which is just that sum of the first 5 million terms. We'll take a look at the actual value, log 2, and then I'm just going to build a percent error. We're not always able to do this because we don't always know what a series converges to, but look at this. Here's our approximation. Here's the actual version. Our percent error is tiny, e to negative 0.07, so that's times 10 to the negative 7th. There's a lot of decimals before this. This is a very, very, very small difference that we have, meaning this is a really good approximation. Now, we're not able to do that in most cases. We can only do that because someone else has already come before us and proved that this series actually converges to log 2. But what this should do is give us good evidence that our strategy is useful, right? Looking at these partial sums and seeing that they don't change that much when we go really far into the tail, that's going to give us really good evidence that our series converges, and also what it converges to. That's new for us. We don't get to say that much when we look at series tests. All right, so here's the examples that you're going to look at. Here's another improper integral. This one, you can see it's got an infinite height because there's a vertical asymptote right in the middle. So you're going to need to split this thing up into two separate integrals, from -1 to 0 and from 0 to 1. Then we've got this cool thing with the gamma function. Oh, I love it. Specifically, we're going to look at this integral. The gamma function is one of my favorite things to talk about in math. It's like a generalization of a factorial, which is so weird. So this value that we get is going to be what half factorial was if factorials made sense for non-integer values. And then for sequences, we've got this weird, janky looking sequence, but that's fine. We're going to do the same kinds of things that we did earlier. Plot some terms, see if the sequence converges, and then look at the series version of it. Plot some partial sums, print out some partial sums, see if we can interpret. You'll notice we won't be able to tell about the accuracy here because we don't know what this thing actually converges to. This is a series that we don't have a nice fancy number like log 2 that this is going to converge to. So we just have to take these approximations and hopefully comment on the accuracy based on our methodology instead of actually being able to compare it. That's all we've got for this lab. Hopefully that was helpful for you to see us just kind of walking through it. If you have questions, drop them over to me in either the Discord or on Canvas. I'd appreciate it on the Discord in the labs channel so everyone can see it, but hopefully that's helpful. Good luck, everybody.